So this is a mysterious story in a couple of different senses. One is this is the first time I've given this particular talk. So it's a mystery to me how it's going to unfold, and I hope it unfolds okay. I mean, you may have seen, if you've heard talks of mine in the past, you may have seen components of it, but the story that links them together is a new one. I should start by acknowledging my collaborator, Darrell Schneider, who has done many of the experiments. This was Darrell when he entered graduate school. He didn't look too happy, but then he won an award, and he looks happier after having won the award. I also should acknowledge...
That's the first LSI ever graduate student award, and there's going to be one each year.
So good for Darrell. He's making me famous. That's his job. I also need to acknowledge the inspiration that I get from my wife and collaborator, James Brodoff, whose interest in stories and causal reasoning underlies the broader story that weaves together the experiments I want to talk about. So she, at least, will see her footprint in the ideas as they unfold. Let's start with Robert Burns, the bard. I have Scottish heritage. My father was born in Glasgow. And this is a poem, To a Mouse, by Robert Burns. In 1785, he was out plowing a field, and he disturbed the nest of a poor little mouse and wrote a poem about it. This is kind of essentially the plot to The Secret of Nim, but 200 years earlier. So what he says essentially is, well, the best laid plans of mice and men often go wrong. I mean, we make these plans, but they kind of mess up. And he's sort of dark and Scottish, so we're left with naught but grief and pain for promised joy. This is just the last two verses of the poem. In the last verse, he says something about plans and the human condition. The mouse lives in the present. The mouse knows about now, but poor Robert Burns can reflect on the past and feel sad about it, and guess about the future and feel sad about it. I don't think we need to feel sad. I think a lot of our joy comes from looking at the future. John Lennon says that life is what happens to you when you're busy making other plans. So what I want to talk about is plans and the role that plans play in controlling our cognitive activities, in controlling our behavior, and controlling our interaction with the world. And there's two kinds of plans. There's two kinds of everything, but just for the purposes of ruling out a bunch of things I'm not going to talk about, is there are cumulative plans where all of the steps you do go together to make some end point, like cooking a meal. You want to have something sitting on the table that your wife is going to find acceptable, and that organizes all of the activities you do, from peeling potatoes to thawing out a big hunk of meat that you then broil while you steam the vegetables. Okay. Those of you who've done grant proposals will know there are endless details that you have to get all right, and they all have to fall together before the grant proposal is a complete thing. So here's a case where the different steps have to be integrated to form some kind of coherent whole. But lots of the time, plans just aren't cumulative. Plans are just a list of things that we have to do. You go into the office on a Monday morning, and there's meetings you have to do, there's email you have to attend to, and you want to get it all done by the end of the day. And it doesn't all add up to anything. It's just a series of things you want to do. Or more, what's perhaps a little more positive, is going on vacation. I'm trying to get the concept of vacation out of the vocabulary of my students and postdocs. But some people sometimes do this. They go away from work. They don't take their computer with them, and they just have fun for a few days. So there's a bunch of things that you want to do, and you don't have specific goals or specific things in mind. I want to go skiing. It doesn't mean I want to go down this hill, this particular hill that I have in mind, and I want to approach this tree and avoid it, and then go over these moguls. You just want to ski. You just kind of set a list of things that you'd like to do, and you want to have fun mostly, and then you kind of tell yourself a story at the end about whether or not it was fun. And these are the kinds of plans that I'd like to study, mostly because they're simpler. It's just a list of things that gives coherence to your behavior. These are the things I'm trying to do, and I want to look at how it is that people carry out these plans. I'm interested in, I'm an attention researcher by training and trade, so I'm interested in capacity limitations. What are the limitations on what we're able to do? We live in a 1-second universe. Every significant event that happens to us lasts anywhere from 100 milliseconds to about 2 seconds. That's the rate at which things unfold. And that's the eye of the needle that our camels have to pass through in daily life. And how is it that we fit these broader schemes, these grand schemes, through this needle hole? How is it we fit them into the 1-second universe? What else is it that limits our plans? Then I want to know what do we do when we're implementing plans? What are the processing that we do that's directed toward the plan itself? When you're carrying out a plan, sometimes you're thinking about the plan, and sometimes you're thinking about the way you're implementing the plan. And I want to look at the interplay between those kinds of things. And I'll end with speculations about what this means for cognitive control and human nature, and if I decide to do it, free will. Okay, so capacity limitations on planning. One of the first ways that people studied capacity limitations was through the memory span task that I believe was developed by Alfred Binet, or at least he was one of the first people to look at individual differences in it. In the memory span task, you get a list of things to remember, often digits. So I give you a list of random digits, and then you have to repeat them back. And your memory span is the maximum number of digits that you can repeat back in correct order. And for college-age adults, the memory span for digits is 7 plus or minus 2. If you're a little kid, it's smaller than that, and as you get older, go through childhood, it increases. So it was a good way for Binet to distinguish the mental age of kids of different chronological ages. So what I'd like to tell you about first is a plan version of the memory span procedure that I call the task span procedure. I give you a list of tasks to do, like judgments that you might do about digits, saying whether they're greater or less than 5, or whether they're odd or even. So I'll give you a list like high, low, odd, even, high, low, odd, even. And then when you have that in memory, I'll give you a series of digits, like 7, 3, 2, 6, 9, and 4. And what you'll have to do is remember the task on the list and do that task on the corresponding digit. So when you got 7, you'd say, well, the first thing in the list was high, low, so I better see whether 7 is greater or less than 5, so I'll say high. Then 3 comes along, you say, okay, it was odd, even, and 3 is odd, and so on. But just to demonstrate it, here's a list length of 4 for you to do, and you need to do this out loud, and we're getting it on videotape, so we'll hunt you down if you don't cooperate. And we'll actually keep score, and if your score is... So there will be a list of 4 task names followed by a list of 4 digits that you have to classify. So here goes. And here come the digits.
Could you move this thing?
Oops, sorry. Good. So you had, at least those of you who replied correctly, have a span of 4. What we did here was to look at, plot the probability of recalling everything, of performing each task on the list correctly. So if you had a list of 4 tasks, this is the probability that you did the 4 tasks correctly. And that is about here. And then you can see, so we're plotting that probability as a function of list length. And traditionally, memory span is the length at which the probability of reproducing the list perfectly is 0.5. So it's like a kind of threshold measure. So here, the solid line is it's labeled the perform condition. This is when you're recalling the tasks and then performing them on the digits that you see. We have a control condition where you get the list of tasks and then you just tell me what the tasks were. You don't have to perform them. And the memory span is a little bit bigger for that, but this was just a small number of subjects run through many sessions. The difference wasn't significant. And often in other experiments, you find a little bit better performance if you're just recalling than if you're recalling and performing, but the increment isn't really large. So the span for tasks here is about 6. The line up here is just running in a single task condition. What's the probability that if you do the same task 10 times in a row, you'll get through the 10 trials without making a mistake. And it turns out to be pretty high, around 0.9. So this is about as good as you can get. And there's this deficit here that comes from having to remember the tasks, and you're kind of you're not doing well at it. So what this is telling us is we can remember about 6 tasks. We can have plans that are about 6 tasks long. It's a kind of capacity limitation that limits our ability to plan. Now, I did this work at Vanderbilt since coming here, and Vanderbilt is a bad place to do individual differences research for 2 reasons. It's bad because we're very selective and we get the upper tail of the distribution. So we're looking at, as George Bush would say, the difference between the haves and the have-mores when we're looking at individual differences. It's also bad because our subject pool is small. There's only 6,000 undergraduates. The subject pool at University of Illinois was something like 6,000. And here it's maybe, 600 or something. And we get about a quarter of them running through our lab. And we'll pay the rest. So if you're interested in making money over the summer, check us out on the SONA system. We're going to be running subjects all summer. And we pay $12 an hour, which isn't quite a free lunch, but it's a cheap lunch. So in another experiment with 64 subjects, we measured memory span and we measured task span, and the correlation was 0.37, which was significantly greater than 0. 0.37 may not seem like a huge correlation, but in the working memory individual differences business, a correlation of about 0.37 is pretty good in the individual differences literature. We also had a measure of switch costs, the cost in performing the task that comes when you have to switch from one task to another relative to repeating the same task, and that correlation turned out to be not significant. So what we're seeing here is a significant component of this verbal short-term memory span impinging on our ability to hold tasks in memory. So we have these capacity limitations, and as a child of the 60s, the first thing that I hear about when I hear about, or I think of when I hear about limitations is, well, how do you get around them? And one way to get around them is chunking. So here is the single task condition, the recall condition, and the perform condition, and we're looking at response time, the time that it takes you to make the response as a function of the trial and the list. So here, for example, is the perform condition. This is the first trial in the list as a function of list length. So here's a list of 1, 2, 3, and up to 10. And so this is how well you did in a list length of 10, or how long it took you to respond in a list length of 10 to the 10th task, and so on. So this is the perform condition where you're having to recall the task names and do the task. And this is just a recall condition where you recall the task names. And what you see is kind of a scalloping in these curves. And that scalloping is a temporal signature of chunking. Chunking is a term that was coined by George Miller in his famous Magical Number 7 paper that he published in 1956. And it refers to imposing a higher level organization, a kind of hierarchical organization on a list of items. So instead of having a list as just a sequence of single elements, you have groups of elements that are kind of jammed together or chunked together. They're in clumps, kind of. And you tend to recall the clumps, and then once you recall a clump, you recall the parts of the clump. And the idea is that each time you get to a new clump, there's an increase in the time that it takes you to make your response, because you have to pull out the clump from memory and then pull the components out of the clump. And then you just rattle off the components and then pull the next component. And the chunks here are in sets of 3, which is a reasonable size for a chunk. It's also reasonable given the particular structure of this experiment. There were sets of 3 tasks, and we used concatenations of the 3 tasks. Or sets of randomly ordered 3 tasks that we concatenated with each other. So there was a structure in terms of 3s. But that's a detail that you don't need to worry too much about. Just the notion is here that there are these chunks. So instead of having to remember 10 tasks, you might just remember 3 chunks. And then when you have to deal with the first chunk, you turn those 3 chunks into 3 tasks and you perform them, and then you retrieve the next chunk and turn it into 3 tasks. So your memory load, what you actually are carrying in your memory, isn't 10 tasks, but like 3 little bits of tasks. And that's a common way that George Miller argued way back in 1956 that we use to get around capacity limitations. And I'll return to that in a bit. The other way to get around capacity limitations is the same way that you get to the Riemann auditorium, and the answer to that is practice. Practice makes perfect, but practice also makes more accurate. So here's an experiment in which people had lists of 1 to 10 tasks to perform. And in the consistent condition, they would do the same list over and over and over again, 10 times. So you get a list of 10 items, and you do it, and then you get the same list of 10 items, and you do them, or task names, and you do them. Then you get the same list of 10 task names again, and you do them, and the same list of 10 task names again, and you do them. This repetition of the list will transfer the information from short-term working memory into long-term memory, so you're no longer going to be limited by the capacity of short-term memory or working memory. You can rely on long-term memory to do the task for you. Here is a condition in which that's like the previous one, in which the list varied from one trial to the next. And you can see there's a limitation in performance. People are doing better here than they did in the other experiment, but still the probability of doing the whole list perfectly declines as list length increases. But in the consistent condition, it's not really much different from the single task condition. If you're doing the same list over and over again, you get to do it. You get to remember everything without being subject to the same capacity limitations. Okay? And what you see to corroborate this story that this is a transfer to long-term memory, that the chunking that we saw earlier is reduced in the long-term memory condition. So here's a condition where you can't transfer things to long-term memory, and you see the scalloping that I showed you before. And here's the case where you can transfer them to long-term memory. You're faster overall, and there's way less scalloping. There's way less chunking going on. Okay. So what does this say? Well, it suggests that plans, or at least these kinds of plans, are held in verbal working memory. Being Canadian, I'm a hockey fan, and being a Nashvilleian, I like to say, I'm a Predators fan, at least so far. And I actually played hockey. I spent my 40s going to hockey. I went to Canadian professional hockey school. It wasn't run by Canadians, and it wasn't run by professionals. But they were like college students from Minnesota, so they were pretty good. At least compared to me, everybody was pretty good. And here I was, 40 years old, skating with 14-year-olds and body checking them into the boards, learning how to do it. And I know that when you're doing something like playing hockey, you have a plan in mind. You kind of know what you want to get a goal ultimately, but you have a plan in mind about how the team is going to go up the ice and penetrate the defensive zone of the opponents. But if you have to put it into words, then you've had it. Anytime you start telling yourself what you're going to do, that's a sign, or at least it was a reliable sign for me that I wasn't going to be able to do it. Sometimes you just act. I mean, it's planful and you're aware. There are players like Wayne Gretzky who had probably 15 IQ points on the next smartest player, who just kind of knew what was going to happen in the game. And there is this kind of intelligence and this foresight that comes out in sporting activities. So there could be plans and activities like that, or plans in playing music. Like if you're doing a solo, you kind of know what the chords are that you're supposed to be covering, but you don't really think, well, I'm going to do these particular notes. Usually you just kind of sit there and watch your fingers do it. But many of the plans that we deal with are plans that we hold in working memory and verbal working memory. We tell ourselves what to do, essentially. And so the planning that we do is subject to the capacity limitations of this working memory, which we know is 7 plus or minus 2, and we can overcome it, as we've shown in these experiments, by chunking. This allows us not to have to plan everything out in detail. You just say, well, you say, I'm going to Colorado, I'm going to go hiking in the hills, and then I'm going to go skiing. You don't have to fill it out in any more detail than that. You can just use those as kind of chunks and fill out the details as you get there. I mean, there are cases where you spell out all of the details. Like when I was planning to declare my love to Jane, I rehearsed the things I would say in endless detail. And of course, it didn't go anything like I rehearsed it at all, as things never do. If you have meetings with the department chair or the dean, you probably do all of this rehearsing too, and then it never comes out that way. It's best often just to deal with the higher level parts of the plan and let the details take care of themselves. As Manny Donchin used to say, you can jump off that bridge when you come to it. Okay. Practice is a way of overcoming capacity limitations, and this is an important component of skill and an important component of automatization, which is something I studied earlier in my career. It allows us to carry out complex sequences of actions without having to think much about them. So, you can tie your shoes without having to think of the details. You can, to some extent, write an essay without having to think of the details, or write an email without thinking of the details. I've seen lots of instances in which people apparently have written emails and hit return and sent them to me when they didn't really look over the details and see what it was they said, because my feelings were hurt. A way that of getting around these capacity limitations is writing them down. As Joe Young, the NSF program officer, used to say, the faintest writing is better than the strongest memory. Things come with instruction manuals, I found out. And if you're a man, you're not supposed to read them. But they come with instruction manuals that tell you actually how to do things. And a lot of things can be prescribed. There's a lot of procedures that can be prescribed in writing. And that's a good way. You can go into lots of extensive detail, and it can be arbitrarily long, just as long as the patience is of the person who's reading it. But that's writing is a hugely important cultural invention that we developed to allow us to carry out plans that are longer than those we can fit into short-term memory. What's interesting to me about this ultimately is that our behavior is being controlled by representations. It's ideas. We're doing things for ideas. What you have in verbal short-term memory is a list of things that you'd like to do. These aren't goals in the sense that they're anticipations of future states of the world, because what you're representing here is, well, I want to judge whether this digit is high or low. So you're not representing yourself pressing the key that says high or representing yourself pressing the key that says low. You're representing the possibility of making that judgment in the future. But it's this representation, it's this idea that's controlling our behavior. And this, I would like to spin on this theme later on at the end of the talk, when I talk about the implications for human nature and free will and so on. Ideas, representations, make things happen. It's like, hey, let's go invade Iraq, and look what happens as a consequence of that. These representations make behavior coherent. So what am I doing? Well, if you ask me what I'm doing, the first thing I'll tell you is what the plan is that I have in mind. And then if you say, well, why are you doing that plan? I'll tell you about some higher level plan. And at some point I'll just go, well, because somebody told me to, or I'll go, I don't know. Randy O'Reilly says we're just middle management, that the plans come from who knows where, and we just deal with these kind of middle level plans, and we get meaning out of filling in the details. These plans, that also suggests that the plans that we have provide causal explanations for our behavior. Why am I doing what I'm doing? Well, I'm doing it because I intended to do it. I meant to do it. My intention, my plan caused me to do what it is I'm doing now. Okay, so how do we do it? As a cognitive psychologist, my job is to identify particular cognitive processes, computational processes, by looking at the inputs they take, the representations that they deal with, and the processes, the computations that they perform on them, and looking at the outputs. And I'm trying to separate in people's behavior the contributions made by different kinds of processes. And when we're talking about planned behavior, when you're carrying out a plan, some of the processing is involved in dealing with the plan itself, and some of the processing is involved in dealing with the object on which you're implementing the plan. So you're remembering, okay, this time I have to do an odd-even judgment. That's a plan-level process. You're retrieving the next thing to do in the plan. And then you look at the digit and you say, oh, 7 is odd. That's what I'm calling a task-level process, because you're dealing with the current input and there's a distinction between them. Here's the plot that I just showed you of response time as a function of trial number, and I talked about the chunking, the scalloping in the graph. What I'd like to point out now are these initiation costs. In all three conditions, the first trial is elongated relative to the others. And if you actually look at the way this unfolds, it appears that what you do when you start a sequence is you rehearse the whole sequence. You run through it in your mind, and then you start. And so the longer the sequence, the longer it takes you to run through it. Short sequences don't take much time to run through. So this is kind of an initiation cost that we go through. We're trying to set ourselves up in order to do a sequence. Well, in this particular experiment, it's confounded. So this initiation cost, the first trial of the sequence, is also the first trial that you execute. So it could be a kind of warm-up effect. I mean, here in the single task condition, you see a speed up. It's not, a slowdown. It's not as big a cost as you're seeing in these other conditions. But here you're just doing the same thing over and over and over again. So why would you slow down? There could be a kind of warm-up effect. So Darrell, Schneider, and I, the color's not coming out here, decided to look at this in a repeated sequence procedure. So people had a sequence of tasks to perform. We showed them circles and squares that were red or blue, although they're coming across as shades of gray here. And they had to iterate through the sequence over and over again. So they get, for example, one group of subjects would get color, form, form, color. The other group of subjects would get color, color, form, form. Somebody else would get form, color, color, form, and so on. We used all possibilities. But the abstract structure is ABBA or AABB. And so we don't have to look at the very first trial they do. We can look at what happens when they get back to the start of the sequences and repeating the sequences. And on the one hand, you might expect there not to be sequence initiation costs here. If you go ABB, 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 sorry, I did that wrong. If you go ABB, AABB, ABB, ABB, AABB, 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 you're just doing AABB. But if you do AABB, 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 it sounds the same. So maybe people will just, if all they're doing is just associating the current stimulus with the previous one or the previous two, which would be enough to disambiguate the sequence and tell you what to do, then there should be no initiation costs. But if they're thinking about this in terms of the sequence, if they have the plan on the one hand and their task level processing on the other, and they're switching between the two of them, then you would see sequence initiation costs. And you do. Here's serial position within the sequence. Here is performance for the AABB sequence, and here's performance for the ABBA sequence. Once you get into the sequence, these are task repetitions. So you've just done A, and now you're doing A again, so you're fast. Now you have to switch to B, so you're slow. There's a switch cost here, a task level switch cost. Now you're doing B again, so you're fast. Whereas in this sequence, this first trial is an alternation. You've done A, now you're doing B, then you get to do B again, and then you switch to A. So you see switch costs here, but in the first serial position, response time is elevated substantially, and this is a kind of sequence initiation cost. So it reflects a kind of hierarchical organization to the person's behavior. They're thinking about what they're doing in terms of the plan, and then they're thinking about the elements of the plan. And each time the sequence repeats, they go back to think about the plan and kind of refresh it, and then go on to carry out the elements of the plan. Okay. This next experiment is Darrell's diabolical experiment. We have a contest going in the lab to see who can make smoke come out of the subject's ears, and this was Darrell's contribution to that. Okay, so you get two sequences, AABB or ABBA, and you're told, well, the first one is sequence 1, and the second one is sequence 2. Now what I want you to do is to do sequence 1, then sequence 2, then sequence 2, then sequence 1. So you would have to do AABB, ABBA, ABBA, AABB. So you have to keep two sequences in mind, and you have to switch between them. And again, what we get is the usual kinds of switch costs once you get into the sequence, and huge initiation costs. But what's interesting in this experiment is when you have to switch between sequences, when you're going from the ABBA sequence to the AABB sequence, or vice versa, you're much slower than if you get to repeat the sequence. If you did ABBA and you're doing ABBA again. So there's this kind of plan level switch cost that we're seeing. Instead of seeing the switch cost just at the task level, I'm slower to perform this particular operation because I just did something different. Now we're seeing plan level switch costs. I've just executed this plan. Now I have to do something different. I've just finished chopping up the vegetables, and now I have to find the crayons for my kid. There's going to be a switch cost there in terms of the switching from one plan to another. This is a kinder, gentler version of the experiment. Again, there were two sequences. We called one alpha and one beta, and we gave people a cue, either the word alpha or the letter alpha, the word beta or the letter beta, that told them which sequence to do. And these cues would come up every 4 trials, and they'd have to carry out the sequence indicated by the cue. And so what you find is that response time is longer in the first position than in subsequent positions. That's partly due to having to process the cue, because the cue occurred in the first positions and not in the subsequent positions. But the important thing is that there's a sequence switch cost. When you had to switch the sequence, you were slower than when you stayed with the same sequence. And that switch cost disappeared in the subsequent positions. Okay. In another version of this experiment, we had people start over. I'll inhibit. There's a joke that's probably inappropriate that is really funny, but I've learned that even if they're really funny, you can still get fired. But so in this experiment, we had people do again sequences of 4 trials, and we'd cue them about the sequence to do. And most of the time, like half of the time, they'd get a cue, and then they'd get 4 trials where they'd carry out that sequence, and then another cue and 4 trials where they carry out that sequence. But on a quarter of the trials, when they got 2 trials into the sequence, we give them a cue again, and that cue would mean start over. Start over either on the same sequence you were just doing, or start over on a different sequence. Okay, so you either had to repeat the same sequence that you had already started, starting it again from the beginning, or you had to abandon that sequence and start a new sequence. On another 25% of the trials, we did that after they'd done the 3rd trial of the sequence. So you get the first one, yep, okay, the second one, yep, okay, and then you do the 3rd one, and then they'd say start over again. And the red lines, if it appears red to you, the line that starts high and ends low is a sequence switch, and the blue line is a sequence repetition. And there are 2 effects here that are noteworthy. One is that when you go back to start a sequence again, there's facilitation. You're faster if you're doing the same sequence than if you're changing sequences. So you can think of this as facilitation from just having done these sequences, or you can think of it as the cost of having to engage a new sequence. But what's interesting is what happens in these subsequent positions right after the switch. There's a cost to doing the same sequence again. It's as if you're stepping through the sequence. Okay, I've done 1, I've done 2, now I have to stop myself from doing 3 and 4. And so when you go back and start again, you do 1, and that's okay, and you do 2, and that's okay, and now you have to do the 3rd one in the sequence, and there's a cost associated with that. There's some inhibition or something that you have to overcome. And you see that here on the 3rd trial and 4th trial when we've switched you after the 2nd trial, and you see it here in the 4th trial when we switch you after 3 trials. That, we think, is pretty cool. Okay, so far, people have been doing sequences, and you can say their behavior is coherent or predictable, maybe not at the level of individual trials. I mean, if you looked at their button presses are pretty random. And if you had them say these things out loud, the sequences of responses, the categorizations might be kind of random. But if you think about the categorization of the category, so they're doing odd, even, or high, low, there's some structure there. What we did in the last experiment I'll talk about is an experiment in which there was no structure to the behavior, sequential structure to the behavior across trials. What we did here is give people 2 lists of sequences. So they're doing color and form. So they might get color, form, color. and the B sequence would be color, color, form, form. And what we would do on each trial is give them a cue that told them which sequence and which item from that sequence to report. So they might get A1, which would mean do the first judgment on the A sequence, which would be a color judgment. So this is supposed to be red, so you'd say red. Then you might get B2, which is doing the second judgment in the B list, which is also color, so you'd say blue. B3 is a form judgment, A2, and so on. Okay, is that clear? So what's happening here is you have these plans in mind, and we're making you either access the same plan over and over again. So, okay, I've got to do the bills, and I've got to pay this bill, the gas bill, and the electric bill, and the cable bill, and the phone bill, but then I also have to, make sure that dinner is going at the same time. So I've got to peel the potatoes and peel the carrots and thaw out the meat. And this is the case where somebody is telling you, now do the gas bill, and then you've done the gas bill, they say, okay, now thaw out the meat. And so if you look at the sequence of behavior that you engage in, there isn't any coherence to it locally. So coherence comes at this more abstract level that, well, it's organized in terms of these two plans that you're switching back and forth between. And what we see here, we did two versions of this experiment. In one version of the experiment, we just told you, we gave you the sequence part of the cue first, and then when the target appeared, you would see the item on the list that you should perform. So you would see, if you were being cued to do the first item on list A, you'd see A, and then you'd see 1 and a blue circle presented after a delay. In this other condition, you would get the entire cue first. So you get A1, and then after a delay, you'd get a blue circle. And we're looking at time course functions, and we're seeing, so this is response time as a function of the interval between the cue and the target. And these results kind of make sense to us in lots of different ways. The lines come from a model that we fitted to the data, and I won't burden you with the details of the model, except that it's brilliant and it fits really well, and it proves that we're right all along and everybody else is wrong, which model should always do. And there's constraints between the models in the two panels that are interesting as well. But the main point is that you see these sequence switch costs. So this is when you switch between sequences, and this is when you access the same sequence. And you see that in both of these different queuing conditions. So even if you aren't following a plan coherently and following a plan step by step, if you have to switch between one kind of plan and another plan, there's a cost associated with it. Okay, so there's this, you're accessing plans and you're not using the plans to organize behavior step by step, but it's still telling you what you're doing next, and there's still a cost, a plan level process associated with that. Okay, these plan level processes appear in measures of task performance. It's not like you do the planning offline and your behavior appears the same whether you planned or not. The time that it takes you to do these plans, to access the plans, to think about the plans, appears in your measure of performance in sequence initiation costs and sequence switch costs. And these plans that we have give structure to behavior. There's a kind of hierarchical control that comes from the plans. There's the plan determines what happens at a lower level of organization. So the plan is kind of like a chunk in a way that makes sense of individual streams of behavior. Okay. So what about cognitive control? Well, one thing we've been thinking about here is the concept of task set. The concept of task set has been an important one in psychology since the 1920s, but it's been particularly important since about 1994 or 1995, when there was a resurgence of interest in task switching, multitasking. You're driving along, talking on your cell phone, and driving your car, drinking your coffee, and you're switching between these activities. Is there a cost associated with it? Well, the answer is yes. And the way the cost is interpreted is in terms of people adopting task sets, which are special states of preparation that enable performance of a task. You might direct attention to a particular part of space. You might prepare certain effectors, like get ready to use your fingers instead of your feet. You might activate certain kinds of knowledge, so you want to know about parity, odd evenness about digits rather than the magnitudes of digits and so on. But there's lots of controversy over what task sets are and whether the switch costs you see in multitasking are actually due to changing task set or due to other things like interference in memory from associations with the stimuli on previous trials. So the fact that I'm slower now to do something because I just did something different could either be because it's taking me time to shift in this new program to do something different, or it could be because, well, I still have this tendency to behave that way, and the responses that are coming out of that tendency are interfering with the responses I have to do now. And that controversy is not resolved. We're thinking that it may be productive, at least. Maybe we're thinking more productive, but we're willing to say just productive, to think about task sets as sets of tasks that you do. This was the concept that of task set that was there in the Lütjens and Lütjens-Einstellung experiments, where you're doing these water jug problems, and you have like 3 jugs, and you have to come up with 6 gallons of water, but one, carries 12, one carries 2, and one carries 3, and there's a combination that you use. So there's a sequence of operations that you have to do, and you kind of develop a habit of doing a sequence of operations. So at that level, what we've shown is switch costs. We've shown that if you have to switch from one sequence of operations to another sequence of operations, that there are costs. And because these are larger operations, each of them taking maybe about a second, we may have a better chance of identifying them and figuring out what it is that's producing the switch costs. So we're kind of optimistic about that. What this research also emphasizes is the role of working memory and long-term memory in cognitive control. We are controlled not only by the stimuli in the environment, but we're controlled by our memory representations. We're controlled by what we're currently thinking about, what's currently on our minds. We're also controlled by our history, the things that we know about, that we've learned in the past about the stimuli that we're dealing with. And a large part of the coherence to our behavior may be explained not in terms of the external stimulus situation, but in terms of the representations we have in our head. And again, it's information that we have in our head. This research is making maybe me more so than Darrell think about the role of language in cognitive control. These representations of plans are mediated by language in a couple of ways. One is we use verbal rehearsal to think about the tasks, and the task names we use are meaningful linguistic labels for the activity or the judgment you have to carry out. So there's a lot of language involved in doing these things. Moreover, we tell people what to do, and they do it. For me, the lab is the perfect universe. It's the one place in the universe where I can tell people what to do, and they'll do it most of the time. And how it is that these 5 minutes of talking to somebody changes their behavior is a huge mystery to me. And if I could understand how that worked, I would have my intellectual curiosity largely satisfied. By contrast, Jeff Shaw downstairs, who studies monkeys and makes monkeys do tasks, well, not quite like these, but similar to other tasks that we've done in the lab, it may take him 5 months of training to get a monkey to do the same thing we can get a person to do with 5 minutes of talking. And that difference is a significant one and an important one to me. But again, language is just a bunch of ideas. So what's powerful about language isn't the components, it's not the articulatory gestures. I mean, we could do the same thing, well, if we had bilingual subjects, we could do the same thing in German or French or Flemish as we do in English and get them to behave in the same way. It's by virtue of the content of the information rather than the physical acts that we express it with. So what about human nature? Again, life is what happens to you while you're busy making other plans. I think what plans do is provide kind of a structure. Well, here's what I was trying. This is one thing I learned from Jane. The canonical structure, the grammar for a story, if you will, is here's what I was trying to do, and then this happened to me. A funny thing happened to me in the way to work today. A funny thing happened to me in the way to the forum. So you have a goal that you're trying to achieve, and then something frustrates it, and you have to do some planning to get around that. The plans that we have give structure and coherence to our behavior, and they're things that we tell other people. And I think largely, my brother-in-law died recently, and I had to do a eulogy for him. And so what I did in the eulogy essentially is tell the story of his life. And it made me think that what our lives are essentially the stories that we can tell about them. What I am is a set of stories. I'm a guy who grew up in Canada, who lived in Champaign for a while. It's a story. I make much more sense at that level of linguistic description, at that level of telling you a story, than I make in terms of a physical kind of being. Sure, I'm a collection of molecules, but the molecules that comprise me now are different from the ones that did, a year ago. But my stories are still the same. So the stories and the plans that we have give structure to the stories, and the stories make up who we are and what we are. This is making me think that what's really in charge at the personal level is information. This is Dawkins' idea of memes that Daniel Dennett has picked up on. We are devices that propagate ideas to each other. What minds do is receive ideas and then replicate them. If you hear a good idea, you have to tell other people. The fun of jokes, for me at least, is in telling them to other people. Oh, here's something, so a meme infects my mind and I go and reproduce it to other people. And it's this action at this level, at the level of ideas, at the level of information, that I think is really interesting. How it is that information can control our behavior is really interesting. Well, free will and determinism. So people who make arguments about determinism are often talking about physical forces and physical causes and trying to reduce things to physical causes. And people who argue against it say, well, it isn't just physical. I think there's something wrong with both of those perspectives. Just looking at things from a purely physical perspective misses the story, literally. So if I reach out and I knock on this thing, a physical description of the impact of my knuckles on the board and the sound that propagates as a result of it doesn't capture the goal behind it or the purpose behind it or the meaning that you take from it. That's something that happens at this level of information. He was trying to illustrate a point. Maybe he did it well, maybe he did it poorly, but the physical description is less important than the cognitive description. On the other hand, informational systems are embodied. Information has to exist in some kind of medium. There has to be some physical instantiation of information. It doesn't just float there. If it floats there in the air, it's in something like radio waves, or it's in something like patterns of compression and rarefaction of molecules that make up the air. Or it can exist in writing, or it can exist in brain states. But information and the physical world are kind of tied really closely together. Who's in charge is ultimately a question that arises with free will. And I would like us, or like myself at least, and perhaps you, to consider the possibility that it's information that's in charge. It's ideas that are in charge. The ideas are telling us what to do. The commander-in-chief tells us where we're going to be deployed, and so we go there. Where do plans come from? The thought pump. So I think we have this endogenous process that just produces ideas. Any kind of memory retrieval process will do this. So memory retrieval processes take inputs and they connect the inputs with associations that are stored in the memory, and they retrieve something. They may not retrieve very much, or what they retrieve may not be coherent, but the process is going all the time. And as Emily Latella said on Saturday Night Live, there's always something. There's always some input. There's always some state of the brain that's going to be serving as input to the retrieval process, and that's going to pull something out. And so what we do is we kind of look at what happens in our heads from the perspective of storytellers. We're storytellers, and we look at what happens and see how we can weave it into a story. This is the human condition. I had this idea walking the streets of Copenhagen in the footsteps of Søren Kierkegaard, who had much more profound thoughts about the human condition on the same sidewalks. So we have this thought pump that's just giving us ideas, and we're making up stories about these ideas. If we like the ideas, then we claim authorship for them. I meant to do that. It's Pee Wee Herman riding through the park, tumbling on his bike, and the kids look at him and he says, I meant to do that. If we don't like them, then we try to change the input so we think of different things. Okay? Plans also come from other people through language, and there's stories that developmentalists will tell about the development of self-control through development of control from other people. So are we special? Is there something special about people? Well, yeah, people convey these stories, but what I think is these stories come out of subpersonal processes that are just kind of, I mean, they're miraculous and mysterious, but they're mundane. They're processes of attention, processes of memory retrieval, and processes of perception. That's what gives rise to the content, and then we tell a story about it. And the people that we know, I think the people that we see, are largely linguistic constructions, where the people that we know and the people that we deal with are things that we talk about and stories that we make up about them. So let me end at that point, and thank you for listening to my story.
Time for some questions.
What time is it? That was clear. Julia?
How do goals fit into that last, the idea of thought pump? I mean, I didn't see goals out there, and your understanding of your goals and your parsing of your goals as what makes that forming those action ideas different than any other kind of thought pump product.
That's a good question. So there has to be some kind of personal commitment to it. I mean, you have to decide that you're going to act upon it somehow. And it's probably means-end thinking. So Randy O'Reilly's notion that we're middle management kind of helps here, that often we start with the presumption that we know what we want to do. You know, I want to have a good time, or I want to get my tax return done, or something like this. And then that acts as a retrieval cue and pulls something out, and then we kind of claim authorship of it or not. We decide, yes, this is something I'll do. This seems like it could work. So, but that's just the story. Andy?
Just make one announcement, which is that this talk will be next week on the LSI website, if anybody wants to see it, and there are other talks that can be gotten from that as well. Now I have a question, and you'll probably laugh at me for this, but back at the very beginning, you were saying things happen like once every second or a fraction of a second. And what was the unit that you were talking about that happens that quickly?
The significant events in our lives, like the actions that we carry out, take about that long. If you look at any kind of reaction time task, half of the psychological literature, the cognitive psychology literature, is based on reaction time. And the reaction times vary from about 150 milliseconds up to about 1,500 or 2,000 milliseconds. For semantic judgments, for naming things, for deciding which line is longer, all sorts of things take about that amount of time. The time that prey are available unfolds. The prey and predator relationships, those events unfold in around that time. I think it has probably got to do with the physics of the medium-sized bodies that we occupy. That things just, there's constraints on how quickly we can move, and we've just adapted to deal with things like that. This is why flies.
So it's a physical thing. Ultimately, it's measured.
Yeah.
It's a physical thing.
Yeah. I mean, flies succeed because. Well, so what we have to be able to do is keep track of what's going on, and things are going to change on us, and we have to be prepared to respond to something that changes. And if it's going to take us much longer than a second to respond to something that changes, it will have changed too much, likely, for us to do it. So we probably develop these ways of making everything quick like that. Yeah. That's my story. Mm-hmm.
I've been fascinated as to why chunking helps us keep more things in working memory. Because if you think of like a computer, say, to remember, say, if you had to remember 9 things, if you had to remember it in like 3 chunks of 3 or 1 chunk of 9, it would seem like it would take like the same amount of disk space.
Well, back when I understood computers, there were so there is like there's RAM and there's the hard there's random access memory, and then there's the hard drive. And random access memory is limited compared to the size of a hard drive. And so all you need to do to keep in the random access memory is just pointers, like file names. So I can keep like 5 or 6 file names available in random access memory, and the files may be, a gigabyte in size or something like that. That all wouldn't fit into there, but if I can keep pointers to them, then I can unfold them. So the idea, chunking is always connected to long-term memory. So you can't chunk things without having formed associations, right? So if I give you a list of letters like NBC, ABC, CBS, you can think of those as 3 television networks. But if I do CBC, CTV, it may not mean anything to you, but if you're Canadian, those would be two television networks. So you have to have this long-term knowledge that allows you to grab things together and pack them together, and then you can just remember only 3 things instead of having to remember 9 things.
So if you give me completely novel digits and I chunk them, then that's how I remember them. That's, even if it's completely novel, that will be stored in long-term memory once it is chunked.
Yeah. The boundary between long and short-term memory is a fuzzy one conceptually. There are people, and some people say there's no difference, and some people say there is a big difference. And the best, the position I like to take on this is the Anders Ericsson and Kinch position, where they talk about long-term working memory that you see in experts. So working memory is essentially the stuff you can access quickly. Things that are in long-term memory, like, what's my social security number? I have to stop for a minute and think about that in order to get it. So it's not immediately accessible like your face is immediately accessible now. But if I'm working in a domain of expertise where I'm looking at things that I'm really familiar with and I know a lot about, then I can retrieve things about them really, really quickly, and it's almost as if they're there currently active. And so with high levels of expertise, working memory capacity kind of expands beyond 7 plus or minus 2 to large numbers. Anders Ericsson did experiments with a guy who had a digit span of 80. And what he would do is recode the digit. He was a runner, and he'd think, so you get 403. He'd think, well, 403 is not a bad time for a mile, and he'd get other numbers and turn them into running things, and then tell himself a story about that, and then use that retrieval structure to pull out what the digits must have been. Pierre?
Yeah, so, maybe related to Matt's question, but at the end also to replace it to the language. So this chunk or this limitation, would you apply the same sort of limitation for a series of 9 actions, for example? You have to move your arm in 9 different locations.
Yeah.
Would you think that the first action would be longer if you have to plan to do 9 actions rather than 6 or 3? And would you start after the third action because it would be a chain of 3 set of action or not?
Yeah.
And my question is because in this set of stimuli, or let's say, probably the language is highly involved. All even, and maybe it's a specific limitation to the language.
Yeah.
And then it's going back to this notion of free will and aspect of story and language. Is that it's just it's a long question, but the thing is babies, for example, or animals doesn't have any language. You can say that's concept, sort of, but they my general question was, did you associate these to language or to any sort of concept?
I'll try to remember the first one too. I think I'm thinking specifically in terms of language, and I don't want to necessarily exclude the other stuff, but with language I know how to think about it. So there's 2 approaches you could take. One approach is to talk about something that's general that would hold for things that do and don't have language. And the other stance to take is let's understand how language works, because language is really powerful, and we know people have it, and we can write down the structure of it really precisely. And if we can understand that, then we will have understood a large chunk of cognitive control, and then that will maybe give us ideas that we can use to make sense of the other things. So it's just kind of a strategy to look at language. And babies are pretty different but babies see events. Darrell Baldwin and Meg Saylor here have done experiments on segmenting actions. So you'll show a baby a videotape of a mother doing something in a kitchen, and if you break it in the middle of an action, the baby will look longer than if you break it at the boundaries of actions. So they're imposing this kind of structure, and then later on they map language onto it, I think. So, and I think these are kids who are about a year old. Do you know what the age is?
Yeah, but they don't need the language. That's why
Yeah.
They have probably a concept because they are capable of organizing these series of actions, but they don't necessarily need the language to do it.
Well, one of the approaches is that you start with the concepts and then you map the words and stuff onto the concepts. So you have ideas of relational structures. Infants will have ideas of relational concepts before they have words that describe them. And then you have this conceptual structure, and then you realize what somebody is using to refer to it. I used to think when our son was little that he came from a non-material universe and he knew everything, and he was just spending 2 years figuring out what language we spoke. He was trying a bunch of different ones and they didn't work, and finally hit on English and it was okay. But yeah, how this comes about is interesting and important. I think it's all, but my stance right now is to let's look at adults and look at their capabilities and see what we can understand from that. I know there are lots of initiation costs that are list length dependent, but the immediate examples that come to mind are work that Saul Sternberg did on typewriting and on speaking lists of syllables, but those are language dependent. I think Eileen Cowler has done stuff with eye movements. But even then, when you're doing like a sequence of eye movements, usually you don't have them planned in advance, right? You just kind of do them on the... You may have, if you're driving a car or something, you may know you want to look in the mirror and you want to look at your speedometer. And you may be looking through those things, but you're not planning a sequence to do it. So maybe if you make people actually do a sequence, then you're making them do language. So yeah, it's interesting to know the role that language plays in that. But if it works, though, if it's just language, then this is then evidence that people are using language. You can use it as a marker for the use of language. Did you have a question? No?
Conversation about emotion and cognitive control. That maybe it's not language per se, but what language is conveying actually is the probability of either an aversive or repetitive outcome. And so what's actually shaping the goal-directed behavior is the probability that you're either going to have a positive or negative outcome. And part of what language does in terms of classical conditioning is you begin to associate particular outcomes with particular language that's being used. And so maybe what this is really about is actually these appetitive and aversive outcomes associated with the goal-directed behavior.
Huh. Yeah, but language causes that. Like, I've been hurt more by words than I have by sticks and stones in my life.
So over the course of your lifetime, there's a certain conditioning such that particular words are associated with particular outcomes. And so language would almost be the medium by which that would be conveyed. Yeah, that's interesting. As a cognitive psychologist, I tend to think of cold cognition, right? Affect isn't important. Cold cognition, affect isn't important, motivation isn't important. Let's just deal with give me the facts, man. But it's as plausible as cold fusion, I think. Okay, well, Jane?
Isn't language just an easy measure of comprehension? So it's comprehension.
Yeah, this is maybe partly what Pierre is getting at, that we have this ability to understand the world. And language gives us a window into that other processes. It's pretty direct because language has components that tell us about the things that we're comprehending. Language is there to ensure comprehension. So yeah, and monkeys can comprehend things, and probably any animal that lives in a significant social environment is doing lots of comprehension and lots of kind of planning and lots of awareness of hierarchies. Okay.
Thanks very much.
Thanks very much.